Hello guys, in today's video we'll see what topological sort is. We'll go through the DFS approach of it. We'll keep BFS for the later time because BFS approach is important as well in this case, because there are questions that can only be solved using the BFS approach of topological sort, but in this case we'll be restricting ourselves to the DFS approach only. Let us first understand what topological sort is. The question wants us to just, we are given with a directed acyclic graph with V vertices and E edges. All we have to do is to return the any one topological order, like any one order of the topological sort. What this toposort actually is. Topological sort tells us the order which will always satisfy the condition. That is, what condition? The condition is if you have started that with 1, all the other nodes behind 1, let's say if we take 1, 0, 2, 3 as an example, in this case one possible topological sort is 1, 2, 3 and 0. Why so? Because 1 is pointing to 0 and 0 is after 1 in the list, satisfied. 2 is pointing to 0 and 2 is before, 1 is before the list, 0, because 1 is pointing to 0. So all the left ones in the array will be pointing to the right ones. Fine. So 3 is also pointing to 0, 2 is also pointing to 0 and 1 is also pointing to 0. Another possible case is 2, 1, 3, 0, or it can be 3, 2, 1, 0. So there can be multiple topological sorts. In this case, since all of them are pointing to 0, all we need to take care of is 0 should be behind any of these elements. So all of these elements. So we do not care the ordering of these three elements because these three are not pointing to each other, and all of them are pointing to 0 only. So 0 is only what you have to take care in this case at least. Now let us go to another example which is a bit more complicated than what this is. Not complicated, but yeah. Okay, fine. So this is the graph we are given 0, 5, 2. Okay, fine. So what we have to, how will form the topological sort? 0, 5 is pointing to 0. So we know that 5 will come before 0 because 5 is pointing to 0. Now 5 is pointing to 2 also. So 5 will, 2 will also come in front of 5. And fine, this case is done. These three, something that we have taken care of as of now. And 2 is pointing to 3. So after 2 is what will have, is when we'll have 3. We are not sure that if it is the right place for 3. All we know is it should happen after 3. That is why we have put it here. And 1 is pointing to 3. So since 1 is pointing to 3, we'll have to put 1 before 3, since 1 is pointing to 3. And 4 is pointing to 1, so we'll have to put 4 before 1. And 4 is also pointing to 0, so 0. So one possible topological sorting order is 5, 2, 4, 1, 3, 0. Let us see what the question is. Okay, fine. 5, 2, 4, 1, 3, 0. So this is also another possible ordering that we can have. All we have to do is to return any one of these. I guess you would have understood what topological sort is. In the directed graph, we know which node is pointing to another node. All we have to maintain is to put the source node before the child node in the vector or wherever we are storing that. So all we have to keep is that in our mind. And why directed acyclic graph? It is because if it is cyclic graph, then there can be cyclic dependency wherein say 1 to 1 is connected to 2 and 2 is connected to 1. So this is a cycle, right? 1 is connected to 2 and 2 is connected to 1. So in the topological sort, 1 comes before 2 and 1 comes after 2. That is contradictory, right? How can 1 come before 2 and after 2, right? Because in our order, either it comes before or comes after, or it comes after. It cannot be both. So because of this contradiction, we cannot have directed acyclic graph in this scenario. And why? We cannot have cyclic graph. And why directed? Because let's say 1 is connected to 2. Had this been indirected, there would be no arrow, right? So one possible path is from 1 to 2, and another possible path is 2 to 1. So it can be 1 to 2 and 2 to 1. This arises another conflicting or contradiction case, as in 1 is before 2 and 1 is after 2, which can be conflictory or contradictory. So we'll ignore these two cases. Hence, only directed acyclic graph is possible for finding out a topological sort. Let us solve this question. It is nothing but what is the intuition of solving this question? We just have to do a DFS traversal, and while traversing it, we'll put the elements inside a stack. That is all what we have to do. So we'll maintain, and then we'll just empty the stack and put that in the resultant vector or any resultant vector, and we'll return that as the answer. So all we have to do is to maintain a stack, and we'll have to do a DFS traversal. Do we have to maintain a visited array? Yeah, we do have to. Visited b is equal to false. Fine, we've done that. We'll pass this visited array, we'll pass this adjacency list, and we'll pass the stack. And what we'll have to do is we'll have to empty the stack. Until the stack is empty, we'll res dot push back st dot top, or we'll name it properly. We'll name topological order. Copy this, and we'll put st dot top in it, and then we'll pop this. We'll do that, and then finally we'll return the same thing. Let me declare this as well. Vector int. Fine, having done that, let us now go to the DFS function itself. Is it returning anything? No, it is not. So DFS, but we'll take the node, we'll take the visited array, we'll take the visited array, and we'll take the adjacency list, and we'll take his stack. Yep, stack int st as reference, and what we'll do is we'll mark visited of node as true, Having done that, we'll traverse its neighbors. From the adjacency list is where we get the neighbors, and we'll, what do we do? We'll call this DFS function again for what? For IT. For IT, only when it is not visited is when we call. If not visited IT, we'll call this DFS of IT visited adjacency and stack. Just before going that, after exploring a node completely, we'll put that st.push the node. Yes, that is all we had to do. Let us compile this now and check if everything is fine. Okay, a column should be there instead of a semicolon. Yep. Let us submit this and see. Easy. Stack bool b false I we just keep on doing that. If not visited of I is only when we call this DFS. Then topological order is correct. Correct. This is also correct. This should work now. I guess you would have understood the approach. That was all for this video. We'll do the DFS version of this in some other video because there are questions that require us to print the, do play with the ordering as well, and that is not possible with the DFS approach. And for that, we'll be using the DFS ordering. And that was all for this video. The time complexity and the space complexity is given. We are following this because this is basically the DFS traversal itself, and the time and space complexity of the same is this. Only that we are using an extra space of stack, so that can be considered, but still the ordering will be same. And that was all for this video. Until next time, thank you.